So I've got this Nippon Pulse tubular linear motor here. The magnets are in the rod, and the coils are in the case here. This is just a flying lead version. Not very clean cabling in this case, but I wanted to test the signal to noise ratio based on violating all the rules. The sensors in here are analog sine cosine, 1 volt peak to peak, just like a sine cosine encoder, which we'd use for commutation and for interpolation on position. And then we'll see on the scope, we'll see the sine and cosine waveforms. This is an ME3 module that has a terminating resistor for the sine cosine and powers the encoder and delivers power to 3 axes. So in this case here, I've braided the wires of the motor power to separate them from the I twisted the pair for the feedback too. So I'll be testing this out with an ACJ drive, another small drive that can do sine cosine. I put in a ferrite. It's a little big. You could use a small ferrite with a couple of turns to get a poor man's filter. So, I mean, this is good enough the way it is. I wouldn't really worry about it, but I'm just sort of pushing the envelope of signal to noise here by mitigating any PWM switching. There is a metal case around the motor, and then there's some tapped holes in here for mounting. So the case will go to earth when you bolt it to the frame. This is like a ACK micro module. This is the 3 axes, so similar size, maybe a little bit smaller, but should be sufficient. We do make a 4 axes, but there's no sine cosine, so let's stick with the ME3 MP3. We'll take a quick peek at some. This is the development board, the JEI ME3 IB1 board. So this is Eric Hodges' board. He laid out, he's a rep of ours that laid this board out for the module. So this is more for the OEM with the EtherCAT drive. And here's the module. Copley makes like you see, a bigger development board. We don't make the OEM board, but just share a reference design. But this is a detailed, like an OEM would lay out. So if it's small quantity, then maybe Eric provides. Yeah, so the motor comes with a spec. It's you got a green dot on one end and a black on the other. Don't swap the rod out, otherwise you'll launch it into outer space. You will get a feedback fault though, because once the sine cosine's missing, then you get a fault. But just put it in properly and phase it properly, and we'll be good. The motor model I'm using here is the SX060Q. So there's all the technical electromechanical specs for the motor. They also provided the 1 volt peak to peak differential sine cosine, which looks pretty good. I've got 120 ohm terminators, so there's a little bit of source impedance drop here, but not much, so less than 10%, which is fine. So this, yeah, don't get the one with the single-ended analog Hall. That's not differential sine cosine plus or minus 1 volt peak to peak differential. I'm laid out connecting sine and cosine differentially to the drive, providing the power to the encoder. There's no shield on the cable. If you did have a shield, just make sure you don't connect the shield to the case of the motor, connect it to the drive, which has earth at the drive. And you can see the sine cosine circuit on the module, and the shield is connected at the drive, not at the motor. And of course, the motor case finds a path to earth here. We'll take a look at the circuit in a moment, but I'm going to go quickly through the normal configuration because it's a little bit peculiar. Brushless linear motor. If you select low frequency analog from the pull down list, then you'll get analog Hall as an option. So it's analog Hall for commutation, low frequency sine cosine. It's just the sine cosine is just shifted to give us the Hall. So just those two is all you need. You don't need Halls, okay? They're analog Halls, and we read them and do interpolation on it. So anyways, the magnetic pair length is 24 millimeters, and it's a 12-bit A to D on this drive. Other drives are 16-bit, but this one is, gosh, it's more like 16 bits of effective. There's a good effective number of bits on the A to D, and it's a sine and cosine. So no, we do not need to give a warning for 4096. I'm doing 1 micron by entering an integer value here, not a power of 2 thing, but a nice round integer to get 0.001 millimeters. That's 1 micron. And I'll show you the accuracy. Never ignore the feedback. There's no break. Position can. Okay. And then the data for the motors entered. So just, newtons of force and Newton meters per amp peak. You could enter the value in RMS. That's fine. But you can see that it's Newton meters per amp peak. And then volts per meter per second. There's a relationship between volts per meter per second and Newton. So it's probably more than 1.3 volts per meter per second. But I never argue with the motor manufacturer. They're never wrong. 13 ohms, yeah, 1.5 millihenry. So, at 2 amps, it's going to be 24 volts. So save yourself some, use a 48 volt supply if you want to go 5 meters a second. I think 2 meters, this wasn't a very fast opportunity. The current loop's all auto-tuned, and I tuned the velocity loop and set the limit to 2 meters per second. Could go faster with higher voltage, but, it's only a short rod, so you can only go so far anyways. But let's make a little bit of a move back and forth here, and we'll see what it looks like. I'm just doing a profile move, 24 millimeters. I'm going to go in the negative direction so I don't shoot the rod out here. And there you go. So I'm going to stop it when it comes back up. So I got repeat and reverse here. And then we'll take a look at it. And oops. Yeah, I'm shooting the rod out again. So let's go negative first. And then I can go positive. Oh, damn it, I did it again. Let's go negative first. Okay. Anyways, back to the camera. We'll take a quick peek at the motion here. So I mean, this rod is I've got it vertically mounted here, so just up and down. You can see the sine cosine, 50 millivolts, 500 millivolts per division is almost hitting 1 volt peak to peak, but it's good enough for what we're doing. It's a very clean signal here. I'm just measuring it like the sine or the cosine differentially. Again, it's doing a 24 millimeter move, which works out to 1 microns, so nice round numbers. You can move any distance you want, of course, and you can even set the resolution higher, but resolution is not accuracy, right? I mean, these are magnets and a rod that are stacked together, so maybe a laser could give you better correction table for, varying lengths on magnets, but I don't have a laser today. Also, there's no bearing in here, so this is just the floating rod. I think there's an option for a little IGUS integral bearing and then an external bearing. A mechanical engineer could hook that up, but this is just for demonstration purposes here. And back to the, making the move here. You can see before we move, there's plus or minus a little bit of counts here. So a couple of, that's not bad. Quantization here and a little bit of signal to noise. And then after the move, you got like a move and settle. Maybe there's a little bounce in here, 4 counts. I don't think that's signal to noise. I think that's just mechanical. But I did do a test to look at the signal to noise ratio. This is while we're disabled. And so this is the quantization. So at about 15 bits of divided by 24,000 for 24 millimeters, 1 micron. I get plus or minus a count and an occasional 2. That's pretty good. And then when the drive's enabled, you see a little bit more noise, so adds maybe another count, so plus or minus 3. And this is, I'm hoping to try to mitigate this a little bit by improving the cabling, grounding, shielding here. But this is pretty good. If we take a peek at the circuit for the receiver, it's a 120 ohm terminator. This will get rid of the fast PWM edges. There's a 7 megahertz filter on differentially. And then this is the filter out, never have more bandwidth than you need, 80 kilohertz. That'll get rid of a lot of the common mode noise too. But if you had a rotary motor and you're doing sine cosine and you're going fast, you might need this bandwidth. So maybe this is a little more bandwidth than you need, but it's still pretty good for our purposes here. It's a diff amp, and it's got a high common mode rejection ratio in a Butterworth filter configuration with some of its own filters here. So multiple stages of filters. So by the time we get into the drive, the signal looks like a really nice sine cosine with a low signal to noise ratio. This move is just a simple move, just for demonstration purposes. We could go a little faster and jog it. So I'm just jogging it up here a little bit. And then to increase the trajectory, I don't know, let me double things a little bit here. And see if this looks good. So I'm going to go down as positive. Yeah, that's a good guess. So yeah, there's a little bouncy. Again, it's a little bit mechanically sloppy here. But as we increase the velocity, we're going to get closer to that goal of, very fast move times. And I haven't done all that much tuning here, but current loop, about 1 kilohertz, velocity loop, a little bit more integral to get us into 0. Proportional gain. There's not a big mass on here, so the default values seem to work pretty good. I turn the feed forward off, so I allow error while I move and settle, because it's a point-to-point move application. I'm going to have to increase my acceleration a little bit to hit a higher speed. So you can see the move times coming down, and we did some moves that are 50 millisecond moves, and then takes a little time to settle, but it depends on your target window. Is it plus or minus 1 micron, and then you're good, or plus or minus 10 counts? So it depends on what you consider in position. So the move is done here, and then the settle is milliseconds later. And if I still have time, I'll keep increasing the jerk on it. The problem with the jerk is it tends to jerk things, so you'll see a little bit more bouncy going on here. So I like to double things a little bit and see what we get out of it. So hitting over 400 millimeters a second, and this is about, yeah, so we're starting to get there. So mechanically, it's a little bouncy, but we're hitting the higher speeds here, and let's try a little bit more acceleration. I think I'm just jerk limited here. Yeah, so I'm not really doing that crazy acceleration except for jerk limited. And as long as I still have recording time here. Oh yeah, there's accel limits, and then there's just a little bit of rounding for the jerk. I think I overdid it here. And let's go faster. 5 times. Yeah, it bounced.